log of x, the common log of x, and ln, the natural log of x. What are their domains when you graph them? 0, I don't know why there's a negative right there. 0 to infinity is the domain. Or x is greater than 0. Okay, x is greater than 0. When you look at their graphs, it only exists for positive x values. They do not exist for negative x values, nor do they exist at 0. How about the range? All real numbers, or if you want to write that in interval notation, negative infinity to positive infinity. Okay, it goes all the way down, and then it increases, but it looks kind of like it levels off, but it doesn't really level off. It just slows in its growth. Okay. How about x and y intercepts? What we got? 1, 0, and none. Okay. So the x-intercept is 1, 0. The y-intercept is none. It never crosses the y-axis. But both of these cross the x-axis at 1. Now, that's kind of related to our exponential function from yesterday. It had the opposite, right? It never crossed the x-axis, and its y-intercept was 0, 1. It's because they're inverses. Okay? They're inverses of each other. So their x and y values switch places. Okay, so that's something we need to know. How about increasing and decreasing? It's always increasing. Okay, these always increase. Our logarithmic functions always increase. So that would be from 0 to infinity, just for its domain. If it's not defined, then we can't talk about it increasing or decreasing. Does it have any extrema? No, because we have no change in increasing and decreasing. Extrema only exists when there's a change. Does it have a vertical asymptote? X equals 0. Now, it's not a rational function, okay? It's not a rational function, but rational functions are not the only functions that can have a vertical asymptote. The definition of a vertical asymptote is just a value that you approach and never touch. So here's kind of what our logarithmic functions look like. They get really, really, really close to the y-axis, but they never touch the y-axis. Or another way of, when you get to calculus, you'll talk about limits, okay? There's a definition for vertical asymptotes in calculus that has to do with limits, but I'm not going to talk about that. All right, how about its end behavior? Okay, how about its end behavior? So can our x values approach negative infinity? No, because we're not defined for negative infinity. But the left side of the function is as x approaches 0, where are our y values going? Negative infinity. As we get close to x equals 0, the y values are going way, way, way down. Okay? And as our x values go to positive infinity, way off to the right, our y values are also going to positive infinity. Very slowly, okay? Logarithmic growth is pretty slow growth, especially compared to exponential growth. Exponential growth is super, super fast. But it will eventually get to positive infinity if we give it enough time. All right, so we're going to look at some operations with logarithmic functions, just like we did with our exponential functions the other day. And we haven't really covered inverses in this class. You should have talked about them some in Math 3. But I already mentioned this. The inverse of the exponential function is the logarithmic function. So here's the relationship here. Log base a of x, okay, log base a of x is equal to y if this exponential expression or relationship exists, okay? X equals a to the y. So the way that I do it, I call it the swoop. If you start with the base and you go around your equal sign and come back to the logarithm, that's going to give you the exponential expression. Base a, y is the exponent, it's equal to x. Okay, but we've got to be able to convert between exponential form and logarithmic form because they're related to each other. As far as this notation here, x has to be greater than 0. We just talked about that with the domain. A also has to be positive. Okay, A is greater than 0 is just a fancy way of saying it has to be positive. We don't deal with negative bases. Okay, we do not deal with negative bases with our logarithms. Our base is always going to be positive. Now, it doesn't always have to be a whole number. Okay, they can be decimals. They can technically be fractions. You don't see that a whole lot. You don't see a whole lot with the decimals. But as long as it's a positive number, it can be the base. And we don't really do 1 either. Because remember we talked about yesterday, if the base of your exponential is 1, that's a very boring exponential function because it's just always going to be equal to 1. Because 1 to any power is 1. So A can't be 1. But any other positive number can be the base. Notice the base of the logarithm and the base of the exponential are always the same number. Okay? The base of the logarithm, the base of the exponential are always the same number. All right, and we read that log base A of x. We have the same relationship with natural log, ln. Okay, that's the natural log of x. It does not have a base. Technically it does. We just never write that it has a base because its base is always e. Okay, the base of the natural log is always e. So if you want to stick a little e in there, you can, but you're never going to see it written there because it's just always e. If it's not e, then we use the common log. The common log, log, is for any other base except for e. All right, same relationship applies there. E to the y equals x is the exponential relationship for that logarithm. Okay? All right, and you put the necklaces up because you're not listening to a word I say. Okay, so what does it mean? Okay, what does all this stuff mean? If we have the expression log base 2 of 8 equals 3, that is true because 2 raised to the third power equals 8. Okay, that's how we figure out what that logarithm is equal to. It's essentially saying, what number do we raise the base to get the number that's inside the logarithm? Okay, so let's do a few problems like that. If we're going to evaluate these logarithms, and we'll talk about the fact that you can use your calculator to do this, but we're going to do it with our minds first because y'all are intelligent. You can do that. Log base 2 of 32. The question is, what power do we raise 2 to get 32? The fifth, yeah. 2 cubed is 8, so 2 to the 4th is 16, so 2 to the 5th is 32. Okay? You're multiplying by 2 every time. So log base 2 of 32 is 5. All right. B, it's just given to you in function notation. F of x is equal to log base 3 of x, and we're saying x is 1. So log base 3 of 1 is equal to 3 to what power is equal to 1? 0. Yay. Oh, that makes me proud as a teacher because I taught some of y'all that. All right. Example C, another function notation here, log base 4 of x. X is 2. We got to think about this one a little bit. We've got to raise, bless you, 4 to some power and get 2. Anybody? 1/2. Okay? Because the 1/2 power is representing the square root. Okay, the 1/2 power is representing the square root. So the square root of 4 is 2. All right, example D, we have the log, no base, of 1 over 100. What is the base of the logarithm when there's not one written there? Base 10, okay, very good. Y'all remember a lot of this from Math 3, so log base 10. So it's saying 10 to what power is 1 over 100? Well, ignore the 1 over for a second. 10 to what power is 100? 2, but it's in the denominator, so how can we get it there? A negative exponent, okay? 10 to the negative second power is 1 over 100. Okay? The natural log. We haven't done a natural log because usually we don't evaluate the natural log without a calculator, except in this case we can because I don't know why. I think it's because one of my high school teachers did it in cursive. and my L's and 1's look a lot alike, so I always write LN in cursive, just so y'all know. So if we've got the natural log of 1, what is its answer? E to what power is 1? 0, okay? That is 0. So here's a note that you need to make. The log base A of 1. So what I'm saying is I don't care what the base is. What is this answer always going to be? 0, okay? Log base A of 1 is equal to 0. It does not matter what the base is. If you're taking the log of 1, the answer is automatically 0. Okay? All right, so I've got a couple of problems there for you to practice with, so please do so. Answer A.